So even though we may learn certain structures of loop, basically there are two broad categories of loop. One is unconditional loop and the second is conditional, finite and infinite loop. So for the unconditional loop, how do we perform the loop? That is quite straightforward, easy. And when we want to do the finite loop, then there are two things that you need to take into consideration. Remember the previous lesson that we did, that you need a loop counter and the loop limit, two things. Now we will learn some of the loop structures, but at the end of it, I will teach you one of my favorite loop structures for finite. So if you know how to do that, the same rules apply for any types of finite loop. So I will share that at the end of, not today's lesson, maybe next week when we have completed the loop, then I'll share that. So the first loop construct that we are going to see is, we have seen in the previous class a bit, is on infinite loop. So infinite loop doesn't have any condition, you just need to loop it. Now the condition, the instruction that we used to do this loop is known as branch. So those instructions, I'm just going to skip few slides here. When we use those instructions falls under control oriented operations. Remember earlier in chapter 1, we have learned byte oriented, bit oriented, control, literal, what else we learned? And also program memory to data memory and vice versa. But we never really learned about control. I said we will see that in chapter 2. And in this chapter 2, here is where it's most relevant. And we use those instructions, the control instructions. Now what does this control instruction do? It will change the program counter. Now in a normal sequence of instructions, what happens is that the PC goes down in the steps of 2 right. It goes down every instruction sequentially. Now when you want to implement a loop, it means that you are changing the content of the PC so that you can perform loop. So what we are doing here is actually, we are going to use instruction to change the program counter. So here in the description, microcontroller executes instruction sequentially in normal condition, as how I just explained. So how many bit is program counter? 21 bit. And because it's 21 bit, this PC program counter is also a special function register. It is divided. If you are having 21 bits, how many registers do you need to hold 21 bits value? 3, because one location can hold 8 bits, right? So 3 file registers means you can hold 24 bits. So out of the 24 bits, you are only using 21. So the names of those registers is PCL, which means PC low, PCH is PC high, and PCU is PC upper. Combine this together, it is known as program counter. Is that okay? Now I will just read through this, then I will explain to you what certain things means. This PCL can be accessed directly, however PCH and PCU are not directly accessible. One can access the value of PCH and PCU indirectly by accessing the PC latch high and PC latch U. Reading the PCL will cause the values of PCH and PCU to be copied into PC latch high and PC latch U. Writing the program will cause the values of PC latch high and PC latch U to be written into PCH and PCU. Now, of course, I will explain what all this means. So in a normal program execution, the PC value is incremented by either 2 or 4. So in normal conditions, always the PC, remember in MPLab we are seeing that it always jumps in a address which skips of 2, right? The PC always jumps in 2 or sometimes 4. Why 4? Yeah, there are some instructions which are 32 bytes, right? So to implement a program loop, the processor needs to change the PC value by a value other than 2 or 4. Because you are moving down 2 or 4. But if you want to do loop, what you're doing, you're changing the PC from the bottom or to go up. That means you're changing the content of the PC. So what are the instructions that we can actually use to change the program counter? So the first one we're going to see is branch n. Now this branch n is one of the instruction associated with unconditional loop. And this branch n works the same like goto. We have seen earlier, right, how goto actually functions. We will also see goto, and we'll see what's the difference between branch and also goto, even though they function the same. So branch n. So what is the description? Jump to the instruction with the address equals to PC plus 2 plus n. So let's see what this means. Okay, let's say we have this series of instruction, sample instruction here. We are going to look at how branch n. Now, what does this n stands for? The n is actually the offset. Branch n is actually the offset, and the offset can be positive or negative. Can you look into, let me see if I still have that here. Yes. So you can look under control oriented instruction. Can you see the branch n? What is the description mentioned? Can you all see? What is it mentioned? Branch unconditionally. And look at the machine code. It is 11010, and then you have n, 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 n. How many bits of n is that? In order for us to try to understand the format, see if I return somewhere here. Yes. This is the control instruction format, which is in chapter 1, and we skipped to wait until chapter 2. So it has opcode, 5 bits of opcode, and 11 bits of n. So what is that n? As I mentioned, is the offset. So how many bits is it? It is 11 bits. Now because the offset, this one, because this offset can either be a positive offset or it can be a negative offset. So when we say positive or negative offset, the n must be able to represent positive and negative numbers, right? So you have seen this formula before? This one. You have seen this before, right? So this is the formula to find the range of maximum positive and negative number. So now considering that we have 11 bits, so what is the range that we can actually go? 11 bits. With 11 bits, you can go 1023 steps. In a while, we will see what we mean by steps. 1023 steps. Okay, in order for you to understand what steps means is that each time the PC is moving, that is known as one step. So that means the PC can move 1023 steps in the opposite, in the positive direction, and it can move 1024 steps in the negative direction. So either you can go reverse up or you can go positive down, forward down. Reverse means it's going to a lesser address. Positive means it's going to a bigger address. All following? So the n is the offset. So the limitation here is that it can go 1023 steps up or you can go 1024 steps down. Is that okay so far? So this is the instruction format. So coming back to here. Let's say we're writing some program here. Start, I'm just simply putting NOP, no operation, and then increase F hex 10. Just a dummy instruction. In this instruction, let us assume it as our S. Remember what is the S? The flowchart just now? Hey, where's my file? Oh, I'm sure I was showing here, right? It's a flowchart that we actually saw. So that is our S. Sorry. So if we were to see the S is this one. This is the task that we want to do. So here, for example, I'm just going to include one single instruction, but the S can be as many instructions as you want. It's not a problem. So after the task is where, do you see this part that it branches back going up? So here is the part where you want to include the control instructions. So here we're going to put branch N. Now let's say, why did I include NOP at the bottom is because after this, when I'm going to show in MPLab, purposely I just added an NOP here so that you can see where the PC is. The PC doesn't disappear, that's all. So now, if in terms of storing these instructions in program memory, do you know why I have started from 001A? Do you know why I started from 001A? Because the last reserved location is 18 and 19, right, for RTFIE. So the starting of address will be 001A. So then when you write start NOP, so 1A and 1B, the NOP will occupy, right? NOP is 16-bit instruction, so it will take up 2 locations. Then what is the next instruction? Increase hex 00. So that will occupy another 2 more locations. And then you have branch N. Branch N is also a 16-bit instruction, so it will occupy another 16-bit. And of course, the last one is NOP. It will occupy the last 16-bit. Just showing you how is it stored. Is that okay? Anything is unclear up to this point? Now, usually, the PC, the green arrow in the MPLab, when you actually press reset, it will actually point to go to start, right? And then when you press F7, it will come here to start. So I'm starting from this point. So by default, PC is pointing here. This PC is pointing to the first address, 001A, which has the label start. And then when you click F7, where will the PC go? The PC will jump by 2, right? 1, it will jump by 2. From here, 1, 2. So, but this movement is known as 1 step. Okay, my one looks so ugly, I step. 1 step. Then you press F7 again. Where it goes? It goes here, branch N. Now, when you press F7 again, when you want to execute branch N, do you remember the definition of PC? PC is actually what? To keep track of the next instruction to be executed. So when you want to execute this branch N instruction, your PC is actually already pointing to the next address. It's already pointing to the next address. That's why earlier in the branch N explanation, it is mentioned branch N changes the content of PC by PC plus 2 plus N. Where is it? This one. Do you see this part? It says PC plus 2. Why plus 2? Because it's already pointing to the next address. That's why it's plus 2. And then plus the N is where the offset comes in. Is that okay? So, let's go back here. When you want to execute branch N, your PC is already pointing to the next location, which is at hex 20. It's already pointing here. Now, let's say this is the task that you want to repeat. So where should the PC go now? Where do you want the PC to go back? This is the task, S is the task that you want to repeat. So you already execute that one time. Now the PC is here. Where do you want the PC to go back? Yes, you actually want it to go back here at 001C. So how much of offset is that? From the current position, this is 1, this is 2. 2 steps, right? It needs to move 2 steps up or down. So it's negative or positive? So it's an offset of -2 from the current location. So what you should write at branch N? You should write here -2. So when you put branch -2, what happens? Currently the PC is pointing at hex 20. It will take an offset of 2 and again the PC will point back at INCF. Are you following? So what will branch -2 do to the PC? So remember just now I was reading all the PCL, PCH and PCU. At this point is where the current location, right? So what will be the content of PC at this point? It will be 0, 0, 0, 0, 2, 0, right? That's the content of the PC. Why the content of PC is this? Because the PC is pointing at this address 0, 0, 2, 0. Therefore the content will be the same. Whatever the content of the PC, that is where the pointer will point. The same concept as FSR. Are you all following? Anything that's unclear? So at this point, the content of the PC is 0, 0, 0, 0, 2, 0. Are you all following? When it executes this branch N, what happens is, remember the PCL you can directly access. That means you can straight away write and read from PCL. But you can't do that with PCU and PCH, and therefore you have the PC latch upper and PC latch high. So what happens during the process of branch, when you execute branch, what happens is that the content of PCL will be copied, the content of PCL is here, but the content of PCH and PCU will be copied to PC latch high and PC latch upper during the execution of this branch. Now that's not the end yet. It will copy and then it will make the amendments. It needs to take this is already what? What is this value? This PC is already PC plus 2 from the current location of branch. Is already plus 2, right? Because it's already pointing ready to the next instruction readily. So when you want to execute that branch, so that's why we are taking this address 0020. So this is already PC plus 2. The actual PC address is supposed to be here 001E plus 2 is already pointing at 0020. And then what will the branch 2 do? So this negative 2, one step, take note that when we want to change the content of PC, the content of PC is not in the terms of steps. The content of PC is in the form of memory address. So here take note that one step is actually equals to 2 memory address, right? Here one step is actually taking 2 memory locations. So therefore, what you should do is, when you want to add the offset to the content of the PC, you take the existing value, which is 000020, plus with the number of steps times 2. So then how many steps that we need to take this now? 2. 2 steps. 2 times 2 is 4. Is it positive or negative? Negative, because you need to go reverse. So even though you're adding the offset, the addition becomes negative. So you are minusing 4. So what is the new value that you will get? So here's 0, this is you borrow 1, you get 16. 16 minus 4 is 12, you get C1C. So this is the new value, right? So what branch 2, this negative 2 will do? It will change this to 1C. After it has changed this, what happens? It will copy back to PCH and copy back to PCU. Is that okay? So what happens here? Of course, this is 1C. So what is the new address? 00001C. Because the content of PC changed, your PC will, from here, will go to 1C. Any question up to this point? So this is how the PC changes its position, because the content is changed. And how the content is changed is because the branch offset value does that. It changes the content of the PC. And because the content of the PC is changed, the PC will jump to the new location. Any question up to this point? Now there is an issue here. The issue here is, now in this case, we have drawn the program memory map here. And then we have listed down the instruction. And therefore we can calculate, okay, how many offset, how many steps is back. But in most of the time, this is not feasible. We won't be able to draw, and this is simple instruction. If you have a lot of instruction, how are you going to draw? So one of the best way is, instead of using offset, you can actually use label. So this part here, this one, so instead of offset value, you use label. When you use label, it makes it very easy. So let's say, where do you want it to branch to? To INCF, right? So instead of writing like this, you can actually write, you can use the label, let's say loop, and you put the label here. Just like how I go to start. Remember, we use the label. Go to start Goto also uses the offset, but since we can't really calculate the offset, we can use label. So when you write branch loop, automatically it will go to loop. So this is an easier way of how we can utilize this unconditional loop. Now let us see the effect in MPLAB. So we're going to write the same thing here. So we're going to have increase F. This is hex 00, and we're going to store the answer back at the file register. Here is where we're going to have branch, and we're going to put here loop, and here I'm just going to put NOP. Where should I write the loop? Here, right? Now let us quick build this. So I need to go to simulation, F6, F7. Okay, let us also try, oops. My bad. And I'm going to view the file register. So you can view the file register content here. So go back here, function 6, 7. So currently we are NOP, and we are going to execute increase. You see increases. Now even though the PC is currently pointing at branch loop, when you execute the branch loop, the PC will automatically point to the next address, which is at NOP. So when you execute here, you can't see that. You can't see that, oh, it's pointing at NOP. But by default, when you want to execute, remember, the PC automatically will try to point to the next. So that is why when we do the calculation, it's PC plus 2. So now when you do this, of course, because we're using the loop, it will go back to loop. So run again. Now the value is 2, 3, 4. So this is an unconditional loop. There's no condition. It will just keep on looping. So you can see the value keep on increasing. Is that okay? So this is how I actually utilize unconditional loop. Now, I just want to show you something before we enter this class. So under program memory, this is the branch loop, right? The branch loop's opcode is D7FE. Take note of that, huh? The branch loop, when we use branch loop, is D7FE. Now I want to show you something. So this is what we get, right? There's now, our case is not branch repeat. We actually used branch loop, DF7E. Now the instruction, machine code instruction for branch is 11010 and as I mentioned, this n is actually the offset value, right? So by right, the offset value was just now was D7FE. So which means this value is your offset, right? DFE. So if you write, 7FE. So when you write it, it is 7FE. Is this value correct? Take note that this is negative. And for negative, we look at the weightage of 0. What is the weightage of 0 here? 1. And we always were plus 1. So what is this value? So is it same with the offset of negative 2? So that is the chapter of unconditional loop.